I've talked about the zeroth law of thermodynamics. So if we count this as 0, so is there a first law or second law of thermodynamics? Yes, there are. There are actually 3 laws of zero dynamics, not counting the 0th law. There's first, second, and third. And I shall look at the first law now. Okay. The first law of thermodynamics. Let's see what this is about. Now, as an example, I'll go back to my picture of a gas with a box that is sort of open at one end, but with a wall that can move up and down, a wall or a piston. Okay, so this side can move up or down, and I have all these molecules of the gas inside. Now, just to make it easy, I'm going to think of this as an oxygen gas again. So that's my oxygen gas. Now let me think about the kind of energies that are involved down here. Now we have already seen the idea of internal energy, which I call U, and which is equal to the total kinetic and potential energy in the gas. Right, so I don't have to just restrict myself to ideal gas this time. It can be any real gas, normal or not normal, whatever. Okay, so we are talking about real world situation now. I just want to start by thinking about whatever internal energy it has. Now the next thing that I want to think about is this. I want to think about heat. Now represent that by the symbol Q usually. So that's heat. Okay. So what is heat? Heat is the transfer of energy, as we have seen, from outside to inside or inside to outside of a body. I can imagine, say, putting this in a bucket of hot water, or putting a fire under it, or even immersing it into a bucket of ice. So in any of those cases, heat will either go in or come out, and so that there is energy involved. Okay. Now, with a gas particularly, with most objects as well, when you heat it, it will expand. So with a solid, not so much, but with a gas, it will expand. It can expand a lot. So it can expand. So if you heat it and it expands, right? Like if you put in heat and it expands, it will do work. All right. If a gas expands, it has to apply a force, say, on one side of its container, and to push it out, it would be doing work. Right? If you remember, work is force times distance. So it has to do work, which I would call W. So broadly speaking, we can see that these three ideas can apply to any real objects. All right, for any real object, you can think about the atoms inside moving, attracting each other, so internal energy. You can think about heating it or cooling it, so heat transfer. You can talk about think about it expanding, or even you can try pushing it down to compress it and do work on the gas instead, or on the spring, or on any body. So there's work involved. So all these three ideas are quite basic, and they can be used for any real life objects. Okay, so now what I want to do now is to think about the relation between these. Okay, now there are various ways to do this in physics. Now what I'm going to do is this. I'm going to think about putting a certain amount of heat into the gas. So I have this heat. Okay, I have this heat. Now I want to put this heat into this gas. When I put this heat into this gas, the gas can get warmer. Okay, it can get warmer. Temperature can increase. And when it does that, the internal energy, the kinetic and potential energies of the molecules would increase. Right, as it warms up, the molecules would move faster, and if it expands and move further apart, they would have to do work against their own attractions, and potential energy would increase. So in any case, when it gets hotter, internal energy would increase. So internal energy would increase. So putting the heat would lead to an increase in the internal energy. And if we allow it to expand, I mean, I can have a closed box, fix the volume and it don't expand. But if I have a movable side, it can expand. And if it expands, it has to do work, right? Force times distance pushes out over distance. It has to do work. So, and that work, energy that's needed for that work has to ultimately come from the heat that I put in. So this heat energy will therefore be used to increase the internal energy and to do work if the gas expands. And that's it. There are no other things involved here. Okay. So what I can do now is I can write down an equation. I can say that heat is equal to the change in internal energy plus the work done. So this is what I'm going to write down now. The heat that goes in is equal to the change in internal energy, and we would use this symbol delta here to represent change plus the work done. So that would mean change. Now when I have an equation, the signs are important, right? Whether it's plus or minus is important. And what this means is we have to be careful about the signs of the heat. Now let's see why there's a sign involved. Now this is the heat that goes in to the gas. Now what if I put this box of gas in ice, right, in something a lot colder? Then heat will go out, and if heat goes out, I should use a negative number here for heat out, for heat going out. So that's how the sign can become involved. And for the work done, this is as I've drawn it, I've talked about the gas expanding and pushing outwards. Okay, so it's the gas that is doing work. But I can have the opposite case where I push down on the piston. If I push down on the piston, I do work on the gas. Right? I would do work on the gas. Okay. So if I do work on the gas, then it is the opposite, and I should use a negative sign for the work done. So so for this equation, the W here is defined as work done by, I'll call it the body. Right? Body in this case is the gas, but it can be a solid or liquid as well. It's the work done by the body. So the word by here is important, and the heat in here is important. It determines the sign of these numbers. So if it's the work done on the body instead, where you're compressing it, I should use a negative sign for the work. And I should also mention that the way I have defined this is only one way to do it. If you look into books, or if you talk to other people who know physics, who know about this, they may prefer to do it by defining Q as the heat out, the heat going out, or define the work as the work done on the body instead of by the body. So in which case, the signs will be changed and the equation would have different signs. Okay, but the important thing here is that as long as we take note of the signs and follow them correctly for a particular equation, it will work. It will work. Now, and finally, I would just point out that this law, which is called the first law of thermodynamics, in this law, you see how I have written down this equation. I've said that when you put in the heat, it is partly used to increase the internal energy, Ke and P, and partly used to do work. And that's all. It's not being used to do anything else. And then I say that therefore they must be equal. Now when I said this, okay, I actually made use of the conservation of energy. All right, if you remember, that law says that energy cannot be created or destroyed. So whatever I put in has to be changed into some other form. And when I add up all those other forms of energies, I must get back the same answer. All right, because if that law, if there was no such law, then they don't have to be equal. Because it can be Q equals to this plus some other parts that has disappeared, and we have no idea. But just because they are exactly equal, okay, this is actually a result of the conservation of energy. So I can say that the first law of thermodynamics is actually obtained. It actually comes from this law of conservation of energy.